Episode 5, Monte Carlo Methods. What if you don't know the rules of the game? In the last episode, dynamic programming computed perfect values by sweeping through every state, using the full transition model. But in the real world, you rarely have that model. Imagine learning to play Blackjack. Nobody hands you the transition probabilities. You just sit down, play hands, win some, lose some, and gradually figure out which decisions work. That's Monte Carlo learning. You play complete episodes, observe the returns, and average them. By the end of this episode, you'll understand how to estimate value functions from nothing but experience. No model, no bootstrapping, just episodes and averages. Let's recall what we've built so far. In Episode 4, we covered dynamic programming, policy evaluation, policy iteration, and value iteration. All three algorithms share the same requirement. They need a complete model of the environment. Every transition probability, every reward, GPI, generalized policy iteration, showed us the pattern. Evaluate, improve, repeat. That pattern stays. But now, we change the evaluation step. Instead of computing expected values from a model, we estimate them from experience. This is the leap from model-based to model-free reinforcement learning. And Monte Carlo methods are the simplest way to make it. Monte Carlo prediction answers a simple question. Given a policy P, what is V pi of S? How good is each state under this policy? The idea is elegant. Follow the policy, play out complete episodes, and for each state you visit, record the return you received from that point onward. The return is the discounted sum. GT equals RT plus 1 plus gamma RT plus 2 plus gamma squared RT plus 3, all the way to the terminal state. After many episodes, average all the returns you've recorded for each state. By the law of large numbers, this average converges to the true value V pi of S. There's a subtle choice here. If the agent visits state S multiple times in a single episode, do you record every visit or just the first? First visit MC counts only the first time S appears in an episode. Every visit MC counts every occurrence. Both converge to the true value. But first visit MC gives unbiased estimates, while every visit MC is biased for finite samples, though the bias vanishes as the number of episodes grows. In practice, we don't store a list of returns and recompute the average. We use an incremental update. After each episode, for every state visited, we update. V of S gets V of S plus 1 over N of S times the quantity G minus V of S. Here, N of S is the visit count. The update nudges V toward the observed return, G. For non-stationary problems, we replace 1 over N with a fixed step size alpha. V of S gets V of S plus alpha times G minus V of S. This gives more weight to recent episodes and lets the estimate track a changing environment. Prediction tells us how good a policy is, but we want to find the best policy. That's the control problem. The first challenge is subtle. Dynamic programming improved the policy by computing Q values from the model. But without a model, we can't compute Q of SA directly. We need to estimate action values, not just state values, so Monte Carlo control works with Q instead of V. For each state action pair visited in an episode, we record the return and average it. Q of SA converges to the true action value. Then we improve. The greedy policy picks the action with the highest Q value in each state. But there's a problem. A greedy policy only takes one action per state. It never tries alternatives. If the initial estimate for action A is higher than action B by luck, the agent will always pick A and never discover that B is actually better. This is the exploration problem. The classic solution is Epsilon-Greedy. With probability 1 minus epsilon, take the greedy action. With probability epsilon, pick a random action. This guarantees that every action gets tried infinitely often, which means every Q value will eventually converge. The full-on policy MC control algorithm combines these pieces. Generate episodes using an Epsilon-Greedy policy. After each episode, update Q values for every state action pair visited. Then update the policy to be Epsilon-Greedy with respect to the new Q values. Evaluate, improve, repeat. It's GPI again. On-policy methods learn about the policy they're following. But what if you want to learn about one policy while following another? This is off-policy learning, and it's more powerful than it sounds. The target policy PI is the one we want to evaluate or improve. It might be the greedy optimal policy. The behavior policy B is the one generating the data. It must be exploratory, trying every action with positive probability. The problem is that episodes generated by B have different probabilities than episodes under pi. A trajectory that B takes frequently might be rare under pi, and vice versa. We need to correct for this mismatch. Importance sampling provides the correction. For each episode, we compute the importance sampling ratio. RGO equals the product over all time steps of pi of a given S divided by B of a given S. This ratio tells us how much more or less likely the trajectory is under the target policy compared to the behavior policy. We then weight each return by its ratio. Ordinary importance sampling divides the weighted sum by the number of episodes. It's unbiased but can have high variance. Weighted importance sampling divides by the sum of the weights instead. It's biased, but the bias vanishes and the variance is much lower. In practice, weighted importance sampling almost always wins. Off-policy methods are the foundation of Q learning, which we'll meet in episode 7. The idea of learning about one policy from another's experience is one of the most powerful concepts in all of reinforcement learning. Let's see Monte Carlo in action on a familiar problem. Our 4x4 grid world from episode 4, but now the agent has no model. It doesn't know the transition probabilities. It can only learn by playing episodes. Each episode starts from a random state and follows an epsilon-greedy policy with epsilon equal to 0.1. The agent moves until it reaches the terminal state at 0, 0, collecting -1 per step. Episode 1 starts at state 3, 3. The agent stumbles right into the wall, down into the wall, then finally left, 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 up, up, up to the terminal. 8 steps. Return from 3, 3. -8, discounted. We update Q for each state action pair along the path. After 10 episodes, the Q values are noisy. Some states have been visited many times, others not at all. After 100 episodes, a pattern emerges. States near the terminal have higher values. The policy is starting to point in the right direction, but not consistently. After 1,000 episodes, the estimated Q values are close to optimal. The epsilon-greedy policy reliably walks toward the terminal, with occasional random detours that keep exploring. Compare this to dynamic programming. DP solved the same grid in 3 policy iteration cycles. Monte Carlo needed 1,000 episodes, but DP required the full model. Monte Carlo learned entirely from experience. Here's the key insight of this episode. Monte Carlo methods replace the model with experience. Instead of computing expectations over all possible transitions, they sample actual episodes and average the results. Think of it this way. The value of a state is defined as the expected return from that state. Dynamic programming computes that expectation analytically using the model. Monte Carlo estimates it empirically by sampling. This trade-off has a name: model-based versus model-free. And it's one of the most important distinctions in reinforcement learning. Model-based methods are efficient when the model is known or easy to learn. Model-free methods work when the model is unknown, complex, or would be harder to learn than the value function itself. Monte Carlo's limitation is that it waits for complete episodes. You can't update values mid-episode because you don't know the return yet. The return only becomes clear when the episode ends. This means MC is best suited for episodic tasks with clear termination. What if you could update after every single step without waiting for the episode to end? That's exactly what temporal difference learning does, and it's coming next. Let's lock in the essentials. First, Monte Carlo prediction estimates V-pi by averaging returns from complete episodes. No model needed. First visit MC is unbiased and converges by the law of large numbers. Second, Monte Carlo control uses Epsilon-Greedy exploration to ensure every action is tried. The agent improves its policy after each episode, its GPI, with sampled evaluation. Third, off-policy methods use importance sampling to learn about one policy from another's data. Weighted importance sampling has lower variance than ordinary. Fourth, Monte Carlo works only for episodic tasks. It must wait for the episode to end before updating values. High variance is the price of model-free learning. In the next episode, we combine the best of dynamic programming and Monte Carlo. What if you could update values after every single step, without waiting for the episode to end, and without needing a model? Temporal difference learning does exactly that. It's the idea that changed everything. See you there.